Use the correlation table. By the way, I keep forgetting to show this to you guys, but on Canvas, you have a practice midterm. It's the summer midterm. So download it when you're done with the unit test, when you're preparing for the midterm, quiz yourself, give yourself 90 minutes. You will be given versions of the NMR and IR correlation tables. They won't be exactly what you see on this correlation table, and I'll point out to you right now the difference. The NMR correlation table had descriptive terms here. Now it's just example structures. IR on your table has an additional column here that clarifies the organic bond type. It gives an example of that bond type. It shows you it in the structure. Now it's just descriptive. So still a lot of information. How much of this should go on your cheat sheet? Like none of it. Because you get that on the exam. These are things I don't want you to necessarily memorize. I want you to know how to use the tool. I want you to know how to reference this correlation table so that you can interpret things about the structures. Should we do this one together, or do you guys want a couple of minutes to look through it to identify the bond types that you see? Okay, good answer. We'll do 60 seconds. 60 seconds to try and find the bond types above 1500 that you think are present. Feel free to look below 1500 if you want to. I'm going to watch the sunset. It's beautiful. Yeah, I thought you were coming to look at the sunset. Yeah, it really is. In fact, I want to have a nice view today. I'm going to hope for this. You guys always get a nice view.
It's beautiful.
Did you say it brings tears to your eyes? Beautiful cloudy sky. What did you say, Mel? That beautiful cloudy sky. This one really has beautiful views. 30 seconds. Find the bond types that you can. Ten, 9, 8, 3, 2, 1. Tell me, what did you find? You found, that's not a bond type, Mel.
Oh my God.
Good effort. Thank you for responding. But carboxylic acid is a functional group. And many functional groups are composed of more than one bond type.
You're asking me to use the 2 brain cells I have.
Right. Ask the other brain cell instead of the one that spoke.
Non-fission.
So you said you think you saw a carboxylic acid. What bond of the carboxylic acid did you think you saw?
There was the OH bond that's at about 3,300. And then there's the C-double-O bond at around 1775.
Okay, so you think that you saw 2 bond types.
Yeah.
Because the carboxylic acid, remember, is this set of atoms, and there's multiple bond types in there. There's the C to O double bond, the C to O single bond, and the O to H bond. Okay, so we think we've got OH and CO double bond. Anybody agree or disagree? Anything else that you want to point out?
Could possibly be sp3CH aliphatic.
sp3ch, okay? Anything else that you guys see? Any feelings you have about the bonds that have been listed? We have what it sounds like are disagreeing. Oops, can't think of the word. Conflicting theories about what this signal is. Seems like Mel is claiming that this is the OH absorption. We see that OH of the carboxylic acid is very broad from the range 33 to 30. From the range 33 to 28. Well, here's 33, here's 28. Those are definitely in that range. Are these signals broad? When you look at the peak, does the peak have a very broad dip before it comes back up? No, it's actually fairly sharp. Comes right down, right back up. The other conflicting assignment here was, I think, what Kiara was giving us, which is 31,000, not 31, excuse me, 3,000 to 2,800, and I've got this set 2 to 3 peaks, being the sp3ch, and we see on the correlation table it should be in that range, 3,000 to 2,800. They both share that range, but the shape tells us that this is more likely sp3ch than OH. Mel, do you agree? Anything else that you guys think might mean something in here, but you're not sure how to analyze it? Anything you're confused on in this spectrum? We can ignore the fingerprint, although if you want to try and look in the fingerprint for meaningful things, we can. Did you guys agree that this signal here, this is 1600, this is 1700, this is 1800. Did you guys agree that this signal here was likely the CO double bond? You do? And we can try to make a guess about what it is. This looks like less than 1750, maybe like 1725, which means that it could be the CO double bond of an ester, a carboxylic acid, a ketone, or an aldehyde. I'm just going to sketch these out for a second. Could be an ester, could be a carboxylic acid, could be a ketone, could be an aldehyde. Just based on where that peak is, it falls in the overlap of those two families. Are there any of these groups that we can rule out and say, it is a CO double bond, but it's not the CO double bond of that functional group?
Probably the original alcohol. So
Not an alcohol.
not an alcohol, the carboxylic acid.
Good, we can rule out carboxylic acid. Why? There's no corresponding signal of the carboxylic acid OH. Remember, those functional groups, they've got corresponding peaks. If you've got one peak of that functional group, you should have the other as well. And we don't have the OH of the carboxylic acid. Anything else we can rule out?
Aldehyde.
How can we rule out the aldehyde, Jackie?
There's no CH bond in 28 or 27.
It's not 28 or 27, is it? It's 28 and 27. Twin peaks, always two. And we don't see those two peaks at 28 and 27. Remember, here's 28, here's 27. There's nothing there. And I know some of you are learning how to read these, and so you're like, well, okay, what is that? What's that? Yeah, that's a fair question. Those are not deep enough. They're not meaningful. This is really a hard part about interpreting spectra, especially experimental, that you've got to get familiar with when to feel confident about claiming that signal and when not to. But those twin peaks, they're always going to be significant. You'll always know when those two peaks are there. Anything else that you guys want to say here? Could be an ester. How do we know?
It has two, right? Or the ester could be between 1775 and 1715.
Oh, we do have that option. Here's an ester or a ketone, right? But how would we be able to differentiate them?
To go off the where you wrote that 1300 between those two really strong peaks.
Yeah. This 1000 to 1300 range, it is in the fingerprint, which means I'm never going to ask you to look for those signals and assign them, because there's a lot of things that absorb down here, but there are a few things that only absorb down here. One of the things that only absorbs down here is the C to O single bond, but it can get lost in the clutter of all of the other things that absorb there. So the C to O single bond absorbs in this range, and we've got two very strong signals. So is one of them C to O? Are both of them C to O? Are they the same C to O absorbing? It's really hard to say. But that might be evidence that there's an ester. Is it possible that it could be a ketone and two ethers? Absolutely. There is no way of knowing that this C to O single bond is the result of an ester connected to this C to O double bond. It could be a ketone and an ether, or two ethers. It could be an ester and an ether. You cannot know. I won't tell you. Anything else that you guys want to point out about this? Anything you're curious might have some meaning? I'm putting question mark because it's in the fingerprint, and this is not something I need you guys to feel incredibly certain about. Anything else? A nitro group? So nitro absorbs twice.
That's in the wrong spot.
Okay. Nitro absorbs at 1550 and 1350. There does seem to be a signal at 1350, but not at 1550.
I read it the wrong side.
You were looking at this one?
Yeah.
Yeah, at 1450. You know, a lot of these are actually more CH absorptions. Like the CH2 WAG and the bending that they do. WAG is an official vibration that bonds have. They wag. How do you say it in the non-Midwest accent? Wag. Wag. They wag. That sounds so silly. I'm surprised nobody asked me about this signal, to be honest. I was waiting for somebody to say, is there NH or OH? Because it looks like there's something in that very high frequency range where OH and NH absorb. And I would have told you, kind of like this, you should probably ignore it. The NH absorbs pretty strongly. The OH absorbs pretty strongly. Okay, can you build a structure? No. Can you even confirm functional groups? Not really. We know there's an sp3ch. That doesn't even mean we have alkane. You guys know methanol technically doesn't have alkane functionality, just alcohol functionality, but it also has sp3ch. So we can't even say for certain that this has alkane. We can say it has a CO double bond, but we haven't actually verified whether it's an ester or a ketone. That's what IR tells you. IR gives you bond types with sometimes ambiguity about what functional groups you have. Okay? All right, so here's the deal. I'm going to draw a couple of compounds on the board, and I want you to tell me which they can and which they cannot be. You don't necessarily have to copy these down if you'd like to. It's okay. But I want you to consider the conversation we just had on the bond types that we know to be present and the likelihood or the possibility of them being any of these. Feel free to chat with each other. Are there any that you know you can rule out? No?
Both of the rings?
Both of the rings. Why can I rule out this one?
That's aromatic ring, right?
That's true.
Oh. I don't know about the second one,
That's okay. That's okay. But why can I rule out this one? What bonds are not evident in my IR?
C double bond C 1600.
C to C double bond at 1600 is gone, as well as the corresponding sp2ch above 3000. That's not present either. Good.
And then the alcohol one.
Can we take out the alcohol?
We can take out the alcohol. We don't have what bond absorption?
The 34 to 3200 range.
Good. The OH of the alcohol is missing. This actually has a C to O single bond, like we think we have down here, but we don't have the OH, so it can't be this compound. Mel, I want to go back to this other ring. What can I use to rule out this ring?
The C to C.
The C to C double bond, and again, the sp2ch double bond. All right, I wanted to put one more in here, but I kind of forgot to. Let's do this one. It looks a little, it always looks funny to me when a carbonyl is upside down. Can I rule out this compound at all?
Does it also contain the C to C that we wouldn't have?
Okay, correct. It contains C to C double bond that we don't have. It's also missing the sp3ch that we know we need to have. That's actually what I meant to go for, but I kind of forgot. It's got peaks we know we don't have. It's got bonds we know we don't have. And it's missing bonds that we know we do have. So it's wrong for multiple reasons. Is there any reason I can rule out this one? It's got sp3ch. It's got ester. Can I rule out this one?
That one doesn't
No, go ahead.
have. No, I'm not sure, but that's actually true though.
That's okay, we can correct it if it's wrong. This one doesn't have. Does it have sp3ch? Lots of it. sp3ch, sp3ch, sp3ch.
That's why I stopped.
That's okay. That's okay. It's always good to point out those things, because if you're thinking it, somebody else might be thinking it too. Does have sp3ch. Does it have CO double bond? And is it a plausible CO double bond? It's not a carboxylic acid and it's not an aldehyde. It's a ketone. And what about this ether? Do I have any room for evidence there might be an ether? Yeah, down here, where it's actually very possible I have two CO double bonds. But again, I'm not asking you guys to be experts in the fingerprint region. I'm never going to give you a problem that hinges on solving the fingerprint region. That means that these two structures, there would be no way of knowing. All right, how many carbons do you think are in this molecule? Five or less? Raise your hand if you think there are 5 or less carbons in this molecule. 8 or less carbons in this molecule? Raise your hand. 10 or less carbons in this molecule? Raise your hand. You guys are, raise your hand if you would never raise your hand because you have no way of ever knowing. Okay. I'm glad I didn't keep going. Here's your compound. Oh, sorry, you really can't see that anymore. What functional groups do you see in there? Not easy to see at all, is it? It's got sp3ch for sure. Not a ketone. What group is that? Ooh, get to know it. Get familiar. Say it louder. Ester. This is ester. It wasn't ester that we had. We had no way of proving that. There was no way to prove it. And what else does it have? It also has an ether. So when we said maybe there are two CO single bond absorptions, that was correct. There were two CO single bond absorptions. One was an ester, one was an ether, but there's no reason that that molecule couldn't have been, there's no reason that molecule couldn't have been a ketone with two ethers. You would have had no way of knowing. Do you guys see the ambiguity that comes with analyzing IR? It's powerful and limited at the same time. I just want you to be comfortable with that. Know that it gives you some information and know that it can't give you all of the information. All right? Cool. We are on our last type of spectroscopy today, and that is mass spectrometry. To be fair, mass spec is arguably, and maybe literally, not spectroscopy. Spectroscopy has to do with measuring light, and mass spectrometry doesn't involve light at all. How was light involved with NMR? Do you remember? How is NMR spectroscopy? How is light involved? Anybody? The nuclei in NMR relax by giving off radio wave frequency light. And the NMR instrument picks up the radio waves. That's light. So that's spectroscopy. IR, how is light involved? How the bonds absorb specific frequencies of IR light in order to stretch, in order to bend, in order to wag. And light is not involved in mass spec, but it's also often grouped in spectroscopy. Also, I'm sorry, I gotta apologize. On Monday, I had the biggest brain fart. I was telling you guys about my research, and I said I dealt with this compound called tetrahydroquinone, and that was not true. I dealt with a compound called tetrahydroxyquinone. What a small difference. Tetrahydrofurane is a very common organic solvent, and I think I just blurred the lines between tetrahydrofurane, tetrahydroxyquinone. This is the starting material of the compound I dealt with, and then it gets reduced down into this compound, which is hexahydroxybenzene. So the name that I gave you and the structure that I drew on the board make no sense at all. And then the other thing I have to apologize for is when I introduced IR, I said infrared absorption spectrometry. To be fair, I don't think that's wrong inherently. Spectrometry is the measurement of a spectrum. Yeah, spectrum measurement. Whereas spectroscopy is measuring light. Microscope, telescope, spectroscopy. So that incorporation of light doesn't forbid it from being measuring a spectrum as well. So I said spectrometry, but it's often called IR spectroscopy. It's the small things. They can mean different things. I just wanted to point that out. I didn't get a lot of sleep that night. All right. Mass spec. This is our last instrumental technique that we'll learn about. And depending on how fast we get through this, I'm hoping we can actually go through some problems of taking multiple spectra and using them to create a compound, figuring out a compound based on its spectra. All right. Here's the basis of how it works. By the way, we have a mass spectrometer downstairs in the organic lab. Those of you that are taking organic lab, you probably hear this really loud vacuum pump all the time. That is the vacuum pump for our mass spectrometer. It needs to operate in very, very low pressure. You need to have like no air molecules floating around. You need to have just your sample. Your sample is input into the instrument. Oftentimes, it may come out of like a column being separated by column chromatography. But your sample gets input into the mass spec, and the first thing that happens is an electron beam is shot at your sample. And this might seem odd, but this electron beam is a little bit more like a BB gun shooting cans off of a log. That electron beam is going to pick off singular electrons in your sample. You're not adding electrons to your sample. You're actually using the electron beam to rip away electrons from your sample. So in this process, an electron is lost and a cation of your sample is formed. Oh, I'm sorry. Not just a cation either, is it? What happens when one electron is formed? Excuse me. What happens when one electron is removed? One electron is left behind from a pair. And that one unpaired electron is called a radical. So this creates a radical cation in your sample. We're going to discuss today how sometimes it's a radical cation in one molecule, and sometimes the radical and the cation break apart, and your compound fragments into two parts. This radical cation is then subjected to a magnetic field. So I'm going to show that magnetic field in a different color. And there are different ways that instruments can be set up. For the sake of visualization, I think that this instrument setup makes the most sense. We're going to have a magnetic field that is curved. You guys remember what B with the arrow means? Just means magnetic field. And you know what interacts in magnetic fields? Charged particles. Things like cations. I watched this really cool video. I didn't save it. I should have brought it in. This guy had a stack of magnets, and then he had a magnetic ball, and he pushed the magnetic ball towards the stack of magnets, and you could see how it actually got drawn in by that magnetic force towards the stack of magnets. And with just the right energy, you could actually get it to orbit. But imagine if you had a heavier ball and you put the exact same energy, it's actually not going to be pulled in quite as hard. Or a lighter ball and the same amount of energy, I think I said that wrong. A heavier ball, same amount of energy, it's not moving as fast, gets pulled in a little bit faster. A lighter ball, same amount of energy, it's going to fly right past the magnetic force. Mass impacts interaction with the magnetic field. So let's say that these fragments, all of your compounds, are moving with the same speed, but they have different masses. Those heavier massed compounds are actually a little bit harder to pull on with the magnetic field because they're moving at the same speed, they've got more momentum. And so they, as they're moving forward, they get drawn in by the magnetic field, and then they hit the detector, but they hit the detector on this far side. If you have a lighter cation moving at the same speed, it has less momentum. It's actually easier to move, so it gets pulled by the magnetic field faster. So you create an instrument with a detector that is segmented off. And depending on where your detector gets hit, you can back calculate from the strength of the magnetic field and the speed of the ions what the mass of that ion was. If my ion hits this side of the detector, that was a fairly light mass ion. But if my ion hit this side of the detector, that was a fairly light, heavy mass ion. And these detectors are incredibly good at what they do. They're very well refined. So you can get down to fractions of an atomic mass unit. If your sample stays together, it gets drawn in by the magnetic field because it's a cation. But if your sample fragments and it creates a radical component and a cation component, only the cation gets drawn in by the magnetic field. The radical is unaffected by the magnetic field, and it just gets sucked in by the vacuum pump, and it goes to the waste. In mass spec, you often analyze a very small number of molecules, like 500 billion molecules. Anybody here good with statistics? Know a little bit about statistics? If I wanted to analyze a sample for how they interact with the electron beam and the masses of the cations that they make, is 500 billion molecules a very small sample set? Is that going to give me good statistics? Do you guys know what's necessary for like a Bell distribution curve? Oh, I don't know about that. I've always heard 30. You need to have at least 30 data points in order to be able to say that you can fit a Bell curve. Less than 30, you don't have a big enough sample. So 500 billion? Good. Why do I say 500 billion is a small number of molecules?
Isn't like the amount of like atoms that you need or molecules you need for like 1 gram of something, like a number to like the 23rd power?
No, not 1 gram. No, one mole is 6.022 times 10 to the 23rd. So if I put in 500 billion molecules, I'm looking at less than half of a mole. Honestly, 500 billion might be a bit of an exaggeration. It might be closer to 500 million. That's not even that number, it's 5 to the 10 to the 8. It's a lot of molecules, but from our perspective, it's like less than a drop. That's how many molecules you're putting into this instrument. But the odds of that electron beam hitting every different electron in the sample is pretty high, except that the compound won't fall apart in every imaginable way. The compound falls apart in very specific ways. And we call that a fragmentation pattern. We're going to look at that in a second. First, the things that can reach the detector. The most important of these is the molecular ion. The molecular ion is always a radical cation. Many of the other fragments that we will look at, well, all of the other fragments we'll look at, but many of the other fragments in the sample are just cations. But the molecular ion is a radical cation. This is if one electron is removed and no sigma bonds break. It's a little bit important. So when that cation hits the detector, how much mass does it have? The mass of the molecule. Gives a signal with the mass of the molecule. That means it's always going to be the heaviest signal on the spectrum. To be fair, sometimes the molecular ion never gets to the detector. So sometimes it's not actually the heaviest signal because it's not on the spectrum. But if it did hit the spectrum, it would be the heaviest signal. And for all the spectra that I will give you, even if it's not a meaningful signal, I'll still show it to you. This is a good example. This has a molecular mass, a molecular ion mass of 216. This stops at 200. Doesn't even go all the way to 216. So the heaviest signal on here is not actually the molecular ion signal. The molecular ion probably never formed a signal. It's just not showing up. But if you were to look all the way at that specific spot, it would be there. The next most important ion for us to consider, actually it's a class. We call these daughter ions. And you can report daughter ions as M, the molecule, minus some number, minus some mass. We're going to look at daughter ions that are M minus 15, M minus 18, M minus 79. These are cations. That have lost a radical fragment. And that radical never shows up because it just flies off and it's not pulled towards the detector. These daughter ions often form alpha cleavages That's meant to be reference to a functional group. Functional groups can either stabilize the cation or they can stabilize the radical. And so functional groups create this high impact zone at the electron beam. For whatever reason, when the electron beam hits the compound, it often plucks out one of the electrons adjacent to the functional group, and then it allows two fragments to form, one with the cation, one with the radical, and the functional group helps to stabilize one or the other. On your correlation table, I've given you some common fragments that form as daughter ions. You'll notice that the bottom has units of mass per charge, m to z. At 15, you see the methyl cation, CH3+, 29, ethyl cation, CH2, CH3+. And then you'll notice that there are two very different fragments that have the exact same mass. At mass 43, you've got this propyl carbonyl cation or this tert butyl. Oh, I'm sorry, 43 is the ethyl carbonyl cation or propyl cation. At 57, a propyl carbonyl cation or a tert butyl cation. And then I believe I made a mistake. This might be something you want to fix. On the very far right side, I show that this benzyl cation, different than the phenyl cation at 77. The benzyl cation, I say it has a mass of 92, has a mass of 91. So close, but not correct. All right, so there's two things I still want to do with you guys. They feel like very different things. Here's what I think I want to do first. I want to come back to fill in examples about daughter ions, so maybe leave some space in your notes for us to fill that in. But I want to talk about the actual spectrum that is created. Along the x-axis, we're finally going to have a normal number distribution. We'll start at 0 on the left, and we'll go to higher mass on the right. The x-axis has units of m per z, mass to charge. M is mass, z is charge. On the y-axis, we'll just put relative intensity. We already said that the heaviest signal is produced by the molecular ion, M plus. Why do we call it N? That's the mass of the molecule. But why do we call it plus? Because it's a cation. It now has a positive charge. Everything else is considered a daughter ion. So I'm going to just draw in some random daughter ions here. Which of them is the tallest? It's obvious, right? The tallest is always set relative to 100. So when we say relative, that's not a straight line at all, is it? When we say relative intensity, we're saying relative to the most abundant signal. 99 times out of 100, the most abundant signal is not the molecular ion. The molecular ion is often hard to form, it's unstable, it doesn't reach the detector often. So we give a name to this most abundant signal. We call this the base peak. That's all the base peak is. It's the most abundant signal. So now that we know that this is m per z on the x-axis, it's also important for us to say the mass that it's weighing is atomic mass units. It's not weighing grams per mole. It is measuring the mass of the molecule that hits. That means it's weighing it in atomic mass units. Because of that, if you have isotopes in your compound, you can actually get each mass of each isotope to show up. That's meaningful because those are going to give different signals m per z because they have different masses. So this is kind of the last thing. I'm still going to come back to some of these daughter ions, but this is the last part, which is isotopic clusters. So first of all, H1 and H2, this is 99.9% and 0.1% of all hydrogen nuclei. So in the case that you have 1,000 molecules coming in, or I should say that differently, 1,000 hydrogens being analyzed, one of them has a heavier mass. That's what creates all of these tiny little bumps on the bottom, is that you've got that 1 in 1,000 chance that a hydrogen is going to have a heavier mass, and that increases the signal relative to the things next to it. Hydrogen isotopic clusters are basically meaningless. And then we've got the carbon 12 and carbon 13. This is 98.9% and 1.1%. That's a little bit more significant. For every 1,000 carbon atoms that you analyze, 11 of them have a heavier mass. Again, that's contributing to all of these tiny little bumps that you see throughout the mass spec. But these are basically meaningless. In fact, the ones I talk about next are the ones that I almost exclusively use mass spec to represent. Chlorine is composed of two isotopes, chlorine 35 and chlorine 37. On the periodic table, you guys will find that chlorine has an average atomic mass of 35.45 AMU. So which of those two isotopes do you think is more abundant? Chlorine 35 is more abundant. In fact, the ratio is about 75% chlorine 35 to 25% chlorine 37, or a 1 to 3 ratio. So if the chlorine atoms or the chlorine ions were ever to hit the detector, they would give this ratio of peaks, 35, 37, with a roughly 1 to 3 ratio. Or 3 to 1 ratio if you're reading it from left to right. The thing is, you will almost never see an isotopic cluster of 3 to 1 at a mass of 35 and a mass of 37, because chlorine doesn't like to be a cation. But if chlorine is a part of the organic structure, then the entire organic structure has this ratio of 3 to 1. So let's look at an example. Let's take a compound like 2-chlorobutane. We've gone to this compound a lot this semester. We did it for a lot of our chirality as well. Here's the mass spec. And here is a 3 to 1 ratio that is 2 mass units off. This is an isotopic cluster, 3 to 1. Do you see any other isotopic clusters?
Is that what it was? No, yep.
It's the wrong way.
Oh, true.
Yeah, because the lighter isotope is more abundant than the heavier isotope. So this is not one of our isotopic clusters for chlorine. Here?
No, that one, like the middle two.
Also off, because this is more like 1 to 1.
Well, the little one next to it, to the right of it, that tall one.
Here and here.
Yeah, would that count?
Well, these are not different by 2 mass units. These are only different by 1 mass unit. And chlorine isotopes are different by 2 mass units. And the masses we're looking at are mass 28 and mass 27 and mass 28. So those can't be organic fragments with chlorine. They can't even be chlorine. Chlorine alone weighs over 30. Does that seem fair? There is one other isotopic cluster. It's much smaller. There you go. Tiny, but it's present. The chlorine isotope, kind of hard to spot. That 3 to 1 ratio, it's not an easy ratio to find, especially like here, where there was this weird signal in between them. The other isotopic cluster that we look at a lot is bromine 79 and bromine 81. Given that bromine has an average atomic mass of 79.9 AMU, which isotope of bromine do you think is more abundant? By how much? By just barely. This is almost 80 AMU. That's nearly a perfect 50-50 split between the two types of bromines, with a skew slightly towards bromine 79. This is 51% bromine 79, 49% bromine 81, and it gives this isotopic cluster that looks nearly 1 to 1. And again, if you could find a signal at 79 and a signal at 81, this is what your ratios would look like. The bromine isotopic cluster is a lot easier to find. By the way, before I leave this example, molecular ion mass, SDBS reports it as, SDBS reports it as 92 AMU, and we actually see this signal at 92 and 94. You can't really see that because it's not given to us, but that is also an isotopic cluster. You also can't tell because they're incredibly small. I know it's an isotopic cluster because it's a molecular ion. And I know it's a molecular ion because it's showing up at the mass of the molecule. And if this is the mass of the molecule, it has one chlorine and one bromine. One chlorine 35 or one chlorine 37. I don't know why I said one bromine. So 75% of the time, it's showing up with chlorine 35. 25% of the time, chlorine 37. Let's look at the same type of compound. No, let's do something different. Let's look at bromobenzene. Mass spec. Do you see any isotopic clusters? I should get rid of this. Any one-to-one isotopic clusters? Yeah, right here. That's a one-to-one isotopic cluster. You can actually see it's not perfectly one-to-one. It's 51 to 49, just barely skewed. And actually right down in here is another one-to-one isotopic cluster. That must be the result of all of those random chances of hydrogen and carbon having heavier masses. Any others that you guys see? How about this one? Little tiny isotopic cluster, meaning that's a fragment that doesn't form often. It does form, just not as much as the others. Yeah? All right. One of the nice things about the bromine isotopic cluster is that it's just so much easier to see. Like, you will get familiar to seeing these clusters of signals, but this one-to-one, two mass unit apart clusters, those are pretty rare. And so bromine stands out really well. One thing that I won't give you very often, but I will say it's something you will come across. When you have more than one bromine or more than one chlorine, you get combinations of isotopes. It's no longer a one-to-one chance that you have bromine 79 or bromine 81. But if you have two bromines in the compound, there is a chance you have two bromine 79s, a chance that you have one bromine 79, one bromine 81, or a chance that you have two bromine 81s. The highest chance that it's two 79s, the lowest chance that it's two 81s. And so the clusters that you form in these cases, they look crazier. Here's a normal one-to-one cluster. That means this is a fragment where one bromine has been broken off, one bromine remains. But this, you know what? I think I misspoke. This is a fragment, a cluster of fragments that have both bromines. This is if you have two 79s. This is if you have a 79 and an 81. Which one is 79, which one is 81, can swap. So there's actually twice as good of a chance that that happens. And this is a fragment where you have two 81s. So it just starts to look crazier. I don't give those to you guys often. Mass spec is just not something we're going to get into a lot. But I want to give you another perspective. If you think the bromine looks bad, just wait for this. When two chlorines are present, maybe it doesn't look as bad. here's the isotopic cluster that two chlorines presents. This is if they're both chlorine 35, if they're both chlorine 37, or if one of them is chlorine 35, the other is 37, or one is 37, the other is 35. That's the cluster that you get. I say this because you might have a homework problem that has 2 chlorines or 2 bromines, and it asks you to identify which one you have by that isotopic cluster. They're not that hard to tell apart, or they're not hard to distinguish. Yeah, they're pretty easy. All right, I think I've talked to you guys for a while. Why don't you guys take a break, and we'll come back to talk more about these daughter ions, okay? The ground's not even totally wet, Will. This afternoon it was pouring. I came up for my lecture at noon, ready to leave to go get lunch, and it was the heaviest downpour. And I did not want to leave because I had no umbrella.
Someone left one in the hallway.
And then an hour later, it was sunny, and like the ground was mostly dry. How does that happen?
Yeah, I thought the state wasn't secret.
It was a desert, huh? Yeah, it has. Literally, 1901 was the last time that Salt Lake City received more rain than 2 weeks ago.
I think we've been breaking the record every year in Ohio for like the past 15 years. Which is crazy.
Yeah. For the first 5,
They're feeling fine. I'm just like my head is just swimming.
yeah, those teachers that are
It's fine.
Yeah.
This is the
Was there a tree on? She was pretty good.
I have gotten the flu once in my life, like a really bad flu, and it knocked me out for like 2 days. And so I get the flu. I don't get sick from the vaccine. I get it like sometimes.
Yeah.
Like, I get loopy fever like it's just people in the shop sometimes, but like that's just stupid stuff. Like tough, but getting the actual flu is probably
No, this one's pouring. Okay. It depends on the molecule.
that might be an indication that
What we're going to look at next is different reactions. How these ions form. And why they form where they form. So this compound has a lot of pi bonds. This is a benzene ring. So it's got those 3 pi bonds.
if anything is like
And it's got a lot of lone pairs. And it turns out that when lone pair electrons are picked off by the electron, or when pi electrons are picked off by the electron, like the molecular ion is very stable.
like I brought the electron to the hospital.
It's kind of like a resonance, yeah. You can see the molecular ion layer is the mass with like this. And so that cluster up there, that's all molecular ions. And that's because one electron can get picked off in a lot of different ways. And the molecule won't fall apart. You have to fall apart. And then it is possible that you actually break off a piece. If you broke off a fluorine, you'd go from 146 to 109, 111. 146 minus 35, so you get to 111. And that's, if I lost one fluorine, I still have the isotopic cluster of the other fluorine. Or if I kicked off both fluorines, I would lose mass of 70, so I go from 146 to 75. In other compounds, it's just so much more likely that you fragment radicals off. It's less likely that you
had it at least twice, but like the one minor transit
absolutely.
people up and like just give it like a really bad pulp or something. Because I just locked myself in a room for a week until I got it.
Question.
Yes.
We know what a primary mean, a secondary mean looks like.
Yeah.
Tertiary.
Easy.
Absorption.
Oh, in absorption. Oh, well,
IR.
remember, amine is a functional group. IR looks at bond types. So in IR, we know that a primary amine, which is NH2, we know that it gives us 2 NH absorption peaks. A primary amine, or I'm sorry, that's a primary amine. A secondary amine has 2 R groups, and this gives us just 1 NH peak. But a tertiary amine, how many NH bonds? So how many NH peaks?
So if you see an absence of a peak, then you know that there's a tertiary amine there.
No.
This one was throwing me off when I was
If you
doing
know
it.
a chemical formula,
Okay.
if your chemical formula has nitrogen, that nitrogen could be primary amine, secondary amine, tertiary amine. That nitrogen could be a nitrile, a cyano group. So you should look for the CN triple bond. That could also be an amide. The amide has the most distinct CO double bond absorption. So you could look at where the CO double bond absorption is, and that might tell you you have an amide. Because in the same way that this is an amine, a primary amide gives a similar shape, a secondary amide gives a similar shape, and a tertiary amide also gives no shape. It's the NH that's doing it. If you have no CN triple bond, you know it's not a nitrile. If you have no CO double bond, you know it's not an amide. And if you also have no NH absorption, then you know it's a tertiary amine. Yeah?
Yeah.
There's a common reagent, triethylamine. Triethylamine would give only sp3ch, some CN somewhere, although your correlation table doesn't talk about it. I think the CN is buried in the fingerprint region, so it's just not useful to try and analyze very well. It's going to give sp3ch, that's pretty much it. And the NMR of this compound, how many signals does it give? The proton NMR. It just gives 2 signals. Because all of these CH2s are identical and all of these CH3s are identical. And if you were to look at the integration and you just find the lowest whole number ratio, it would give it to you as 2 to 3 because they're all symmetric to each other. When in reality, it's not 2 to 3, it's actually 6 to 9. It's some ratio of them. So that would be a very challenging molecule to try and deduce from its NMR and its IR. Not impossible, just really challenging. Because you wouldn't see this, which I guess would tell you you don't have any of those.
True.
So you have to draw a structure that doesn't have NH. Yeah, if you see if you see the absence of an NH, it doesn't mean you have a tertiary amine. You still have to have a nitrogen in the chemical formula. Good question.
That was in my structure for assignment 3.
You have a tertiary amine.
Yeah. I was
Lidocaine.
like, what the hell do I do with it?
Yeah. No absorption. You could see if the CN will absorb, but you would not expect this absorption. Good. All right. So I was saying earlier, I wanted to show you guys the daughter ions. I think, actually, this is what I would be showing you. It's the correlation table. So I think what I want to go through right now is the formation of these ions. So we're going to look at the formation of the molecular ions and the formation of the daughter ions. And I think I'd like to start with bromobenzene. No, I don't want to start with bromobenzene. I want to give you guys something good. I think let's look at an amino acid. Anybody know amino acids? You guys have a favorite amino acid? Tryptophan is always a good one. Oh, it's not showing me the structure of tryptophan. Oh, tryptophan is a long molecule. I don't necessarily need you guys to look at this long molecule. Let's just go with a good old alanine. Alanine is a much smaller structure. Alanine is this. Oh, and a methyl group, CH3. I knew something felt wrong about that. All right, so we're looking at the mass spectrum of alanine. I want to show you guys all the different ways that electrons can get picked off of here. The molecular ion is best formed when electrons are lost from a lone pair or a pi bond, and lastly, a sigma bond. There are a lot of lone pairs in alanine that I could choose from. How many lone pairs? Is there at least one lone pair? They're not drawn, right? This is something you need to know. There's 2 lone pairs? There's 5 lone pairs? I can't hear you. There's at least 2 pairs on each oxygen, and there's 1 on the nitrogen. 5 lone pairs. I could show this with any of those 5 lone pairs. Let's show it with the nitrogen. If one of nitrogen's lone pairs is pulled off, if one of nitrogen's lone pair electrons is pulled off, it goes from being a pair to a radical. And the nitrogen now holds a positive charge because one of its electrons was lost. That is a radical cation. You see how it is both a cation and has a radical electron. And so it gets pulled by the magnetic field to the detector. And how much does the molecule weigh? 89. It hit the detector at 89. That gives a signal of 89 m per z. I could also have formed this by pulling away a pi electron. How many pi electrons in alanine? 2 pi electrons, 1 pi bond. If I pull away one of those pi electrons, which of the atoms in the pi bond is more likely to lose it? And which atom is more likely to keep the radical? Oxygen is more electronegative.
Yeah.
Oxygen is more likely to keep electrons. So the oxygen takes the radical left over from the pi bond, and the carbon takes on a positive charge. I had 2 electrons between C and O that were pi electrons. I lost one of them. One stays as a radical, and one carbon has lost both of them. All right, lastly, I could rip away a sigma bond. How many sigma bonds in alanine? 5? Elise is like, no. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12. Gotta count all those hydrogens. I gotta tell you, one of the most missed questions on this summer's midterm was how many sigma bonds were in a compound like this. Easy mistake. What did we say? 12. There are 12 sigma bonds. So there are a lot of places where I could pull away a sigma electron. No?
Wasn't there another H on carbon?
I counted this one.
In the middle with the oxygen?
No.
No. Oh, because that's a carbon.
How many bonds do you see already going to that carbon?
Oh, 4.
4. There you go. I could pull this from a lot of places. Do you agree? I'm going to pull this from this sigma bond, the carbon-carbon sigma bond. I could pull it from anywhere. Here's what the molecular ion would need to look like. Yikes. That is a 1 electron covalent bond. That's what you are proposing. Me. That's one of the possibilities of how that molecular ion forms. Of these 3, which is the most stable? Well, this is pretty stable. I'm not even close to breaking a sigma bond. This is pretty stable. I also haven't broken a sigma bond. This is incredibly unstable. I've got 2 atoms that are fighting for 1 electron, and if one of them gets blown away by the wind, I don't have a molecule anymore. I have fragments of a molecule. These are 3 possible ways that the molecule can reach the detector as a molecular ion. And all of these give the signal 89 m per z. On your unit tests, on your midterm, I like to give questions like this, which are, which structure below does not produce the molecular ion? And then I show you a number of different correct ways the molecular ion can form, and I show you a fragment. It's not a radical cation. I also want to point out these radical cations, they all look different. Here's a radical cation on the nitrogen atom. Here's a radical cation between the carbon and oxygen. And here's a radical cation within the carbon-carbon bond. So they look different. The radical cation can take on all of these different forms. That's formation of the molecular ion. But let's take a look at different ways the daughter ions can form. Here's a common daughter ion that I want you guys to be familiar with. M minus 15. The molecule less the mass of 15. Use your correlation table. And remember, this is the correlation table I won't give you on the exam because I really feel like it's the least useful and it takes up space. What fragment has a mass of 15? Methyl. So if this is the molecule minus a mass of 15, then I'm looking at a cation where the methyl is not a part of it. So I take this CH3 group of alanine, junk, gone. Literally, where is it? It has the radical. It has the radical, it's CH3 radical. Does the CH3 radical show up on the detector? No, radicals aren't cations. Only cations get drawn to the detector. Radicals don't make a signal. So we're looking at the molecule less 15. Can you tell me what mass this actually hits as? 89 minus 15, 74 mass per charge units. That's this signal right here in alanine's mass spec. This, here's 89 molecular ion. Here's M minus 15. Okay? What about this structure? The base peak. This has a mass of 43. No, 45. Yes, 44. You know what? I don't like that a lot because the fact that it has 44 tells me the nitrogen is doing something funky, so I don't want you guys to have to worry about that very much. But if we were to name that in terms of M minus something, what would we call it? Is it M minus 44? It's the M minus 45. That would be the name of the signal. The molecule less 45 mass. All right, let's look at some other ones. Let's look at the M minus, let's do some alpha cleavage. Okay, here I've got a functional group. I could cleave off that functional group. But here I have another functional group. I've got the carboxylic acid. So let's look at what happens when this bond gets cleaved. So I'm going to lose CH3, CH, and NH2. CH3 has a mass of 15. CH has a mass of 13. NH2 has a mass of 16. So 15 and 13 is 28, 38, 42. So let's look at the M minus 42 signal.
Would it be 44?
Yes, 44. Oh, actually, we might be onto something. Sorry, M minus 44. I want you guys to notice this is the same bond that I broke last time. I'm breaking that carbon-carbon bond again. But this time I'm actually just going to form two fragments. The M minus 44 fragment is this component where I've also lost this as the radical. This has a mass of 45. All right, well, now that we're here, let's show the M minus 45 signal. Let's show the structure that gives the M minus 45 signal. I'll give you a hint. It's already on the board. You just need to change where the radical is and where the cation is. What is the structure that gives this signal at M minus 45? Anybody want to try and describe it?
It's where you have the plus is where the radical is.
Yeah.
Yep.
And then when I make that a radical, that's what makes the signal? Radicals don't make signals. Cations make signals. So it's where I have the radical, if I make that a cation, that produces the signal. This has a mass of 44 m per z. This doesn't hit the detector. Andy, can you tell me why it doesn't hit the detector? Because it's a radical, it's not a cation. Will never hit the detector. So here's how I like to phrase this. I like to frame this in a way. If you pick off a sigma electron, like I did here, I picked off this sigma electron. This is not very stable. So which way is it going to move? Will the radical go with this side and become a radical fragment here, leaving this carbon as a cation? Or will the radical fall on this side, leaving the cation on this to get a signal? Both can happen. But typically, one happens more readily than the other. And there's actually reason behind it. There's a resonance reason. I don't know that this is going to be the best example of why resonance does it, but this nitrogen can actually share in resonance with that carbon cation, and it maximizes octets. That's always a good thing. But actually, this can do it too. I didn't actually draw the geometry of this fragment correctly. I did it so that you guys would recognize it. But that carbon only has 2 electron regions. That's sp hybridized. That's a linear geometry. And so you can show a resonance form like this. So technically both fragments have resonance stabilization of the positive charge. This is why alpha cleavage is so common, because the heteroatom that is alpha to the cleavage, next to the cleavage, usually has lone pairs that can stabilize the positive charge that forms. Just turns out that nitrogen here stabilizes it better than oxygen here. That should actually make sense. Nitrogen is less electronegative. Nitrogen shares electrons better than oxygen does. Okay? What questions do you have on mass spec still? I'd like you to show me a molecular ion that can form for this 1,4-dichlorobenzene. And I'd like you to show me the M-35 structure for this compound as well. How many different ways can you draw an M+ structure? Like a billion here. You could all probably draw a different structure. No, that's not true, but there's a lot. When you think you have one, turn to a neighbor and compare your structures. Are they the same? Do you agree that they both work? Okay, I'm sorry. I also want you guys to admire the beauty of this sunset. You see that? Oh, where is that? It's like, that's something from a painting, right? Beautiful. There's a lot of chemistry going on in there. Oh, so much. You wouldn't even believe it.
The mindset there is everything.
I watched a video today that was like a marine biologist talking about how special the ocean is. She's like, imagine if we didn't have the blue, the great blue. What would we do without water? I was like, oh, water is not blue, actually. Do you guys know why the ocean is blue?
It reflects the
It's reflecting the sky. Water is clear. No, the sky is blue because of how different wavelengths of light scatter between the molecules. The shorter the wavelength, the more they scatter. No. Yeah, the shorter the wavelength, the more they scatter. Scattering is inversely proportional to the square of the wavelength.
What if this whole time the sky was reflecting the water?
Yeah, then I'd be surprised.
Now
All right.
we're getting somewhere.
How many structures did you guys come up with? Any of you agree on them? Tell me a structure I should draw up here for M plus. What did you decide to do? You took a lone pair off the chlorine. And since we don't draw lone pairs, that meant that you had to draw in a radical plus the positive charge. We always show radicals. We can assume lone pairs, but not radicals. Did anybody draw a different M plus?
You can also do it on the other chlorine.
On the other chlorine as well, correct?
She broke that double bond.
Broke a double bond. And there are a lot of double bonds to break. And so there's a lot of different ways you could show this. But I could show this double bond breaking, and I can get a radical and cation pair there. I could actually break the exact same pair of electrons, and I could just swap where my positive and my negative are. And then, of course, I could break a pi bond that is not adjacent to either of the chlorines, and in which case, no matter how I place it, they're going to look the same. All of those are perfectly acceptable molecular ions. I think the one that I would have said is maybe theoretically not possible is if you had done something like this. Try to break one of the sigma bonds. Pi bonds just break so much easier than sigma bonds. And technically there's a double bond in resonance all the way around the ring. So yeah, I mean, I get the idea, but that would be the one I wouldn't write down on your notes either. I wouldn't go for that one. All right, what about M minus 35? What did you guys draw? Good. And made what? What became the radical? Chlorine became the radical. So a positive charge on the carbon. And of course, you wouldn't see this, but you get a chlorine radical. Is there any other way to do it?
You can also break off the other chlorine.
Break off the other chlorine. And this N minus 35, true or false? It gives a 3-to-1 isotopic cluster. Let me phrase this a little bit differently. Is the M minus 35 is the M minus 35 signal going to look like this, or will it just be one signal? 3-to-1, 1-to-1, or just one signal? No, that's a good point. When we remove a halogen, we just remove the lower mass halogen. In fact, when you look on here and you say the molecular ion is this, the molecular ion is not using the average atomic mass. The molecular ion is using the lowest
So we're knocking
isotopic.
off the 35 chlorine.
You're lobbing off a chlorine,
Yeah.
and you still have a chlorine. And remember, your sample size is a few 100 million molecules. So how many times will this remaining chlorine be 35? How many times will this remaining chlorine be 37? 3-to-1. Always. So this signal, it's not 1-to-1, that's a bromine isotopic cluster. And it's not just one signal, because the chlorine is present as 2 different isotopes, different percents of the time. based on the mass spec that you see in front of you, does this chemical formula contain a bromine or a chlorine? Your best guess. Does this chemical formula, does this compound, contain a bromine or a chlorine? You see a bromine? Where do you see it? How much does bromine weigh? 79 or 81. And you think you're seeing a isotopic cluster at 50 something?
That's stupid, I'm sorry.
Good catch.
I see one.
81. Isotopic cluster for bromine has what shape? 1-to-1. I don't see 1-to-1 peaks.
81.
Here? Like 80, 81. Okay, you're saying 81 and 82 or 83? Okay, so bromine weighs 79 and 81. So to have a mass at 81 and 83 means that this is Br bonded to what organic compound? H2? No. It's a good guess, but again, I think just going on molecular mass, no, those can't be bromine isotopic clusters.
I think that's the only possible place that could have been.
I agree. No isotopic clusters here for bromine. Any for chlorine? No?
Around
70. These two?
yes.
They're 1 mass unit apart, but chlorine and bromine isotopes are all 2 mass units apart. You know what I mean? So 1 mass unit apart wouldn't work. I see like the similarity in height, although this looks maybe more like 1 to 2 instead of 1 to 3. Anything else? No isotopes here. No bromine, no chlorine. In fact, here's your chemical formula. C6H12O. That's the chemical formula that we're going to be working with. Now here's what I'd like you guys to try and do in these last few minutes. Here is the NMR and the IR of this compound. Can you see? Okay. Oh. Can we try to figure out what this compound is? What should you do first with this chemical formula?
Figure out which molecule the
Degrees of unsaturation. I need to know if there's a pi bond in here. I need to know if there's a ring in here. Or I need to know if there are none of those. So degrees of unsaturation, 2 chicken rule, 2 times 6 minus 12. There are 0 halogens, there are 0 nitrogens, and then I always add 2. Multiply by 2, subtract by 2, add by 2. What's the last thing I do? Divide by 2. 12 minus 12, 0. 2 divided by 2, 1. Does this 1 degree of unsaturation come from a pi bond? Should I look at the NMR or should I look at the IR? I think the IR, because I can look for CC double bonds and I can look for CO double bonds in the IR. Correlation table time. Where can I find CO double bonds? That's a pretty narrow range. More like 16, 15 to 18 something. 18, 20. So this range, this is my CO double bond range. Anything? I mean, there's that little guy, but you should ignore that. Why? Because CO double bonds are always the strongest absorption. There's nothing here. No CO double bond. Is there a CC double bond? I can look at 1600. I don't see anything. I can look up to 1700. That's a little high, to be honest. It's a little out of range for CC double bonds. If it is a CC double bond, I should also expect to find sp2ch signals as well. That's a corresponding peak. So if I think that is a CC double bond, I should look for sp2ch. Any sp2ch? Where's my cutoff for sp2ch? Where should I look? That was hard on the eyes. 3,000 to 3,150. So here's 3,000. Anything there? Empty. What is this? OH, not alcohol. OH of the alcohol. So you were like 50% right. OH of the alcohol, as opposed to the CO of the alcohol. What's this? It's too high for the aldehyde. It's not at 27 and 28. This is between 28 and 3,000. What's that? The most common bond type in all of organic chemistry, sp3ch. But any evidence of an sp2ch? I should have seen a signal right here, and there's nothing there. Okay, well here's something. What's that guy? I'm going to ignore it. Because if that looks like the CH of an aldehyde, I know I don't have an aldehyde. There's no CO. So do we think there's a pi bond here? I'm going to say no. And actually, I can go back to NMR to try and confirm that. If there was an alkene, I should have a vanillic signal in the 4 to 6 region. I don't. If there was an aromatic ring, I should have it in the 6 to 8 region. I don't. If there was an aldehyde or a carboxylic acid, I should have it in the 9 to 12 region, and I don't. I know you can't see all the way out there, but there was no signal there. So this is what then? This is a ring. I have a ring in this structure. This ring might be a 6-membered ring with an alcohol coming off. It could be a 5-membered ring with an alcohol and a methyl. It could be a 4-membered ring with an alcohol and 2 methyls or 1 ethyl. It could be a 3-membered ring with an alcohol and 3 methyls or 1 ethyl and 1 methyl or 1 propyl. You guys remember structural isomerism, right? So now we look at this. Here's 1H, 1H, and I'm just going to give you that this whole region here integrates to 10H. Which means I'm not telling you that there's a specific CH3 signal. If there's no specific CH3, there's probably no methyl group. I could have also given it to you like this, 2H, 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 4H. That gives you a lot more confidence that there's no CH3. There's no methyl group. If there's no methyl group, then it's very likely that you've got this 6-membered ring. But what's this? Why is it so far over? It's by the alcohol. It's not the alcohol, because although it doesn't look like it, it's split. If it wasn't split, it'd be much taller, like this 1H. So why would this 1H not be split? This is the alcohol. Remember that hydrogens on alcohols and amines don't split. They don't have multiplicity. always just one peak. Why is this so far left? Functional group adjacent. This is the hydrogen next to an alcohol. And then I've got two H's all the way around. That gives me this 10H group. Now, you could have also tried to reason that this is a 5-membered ring with a CH2OH, but that would have given you 2 hydrogens functional group adjacent. That's not going to work. And it would have given you a 1 hydrogen signal that is not functional group adjacent. So play around with the structural isomers to prove that this makes the most sense. This weekend, you will have a problem. I'm so sorry, guys. You will have a problem. Your part B is analyzing IR, analyzing NMR, and building a structure from a chemical formula. And once you've drawn a structure, whether it's correct or not, draw a molecular ion for the structure that you've determined. It's going to be tying all of these pieces together. When is your thing due? Your unit test. It's due Sunday night. Monday, come in with questions. We're going to review Monday, but I don't know what you want to review most, so come in to review. By the way, with the unit test, I have uploaded pictures, screenshots of SDBS spectra, and I've gotten feedback in the past that they look terrible. So I've also uploaded PDFs of those screenshots that have much higher quality. You should be able to download them and view them to get a better reading on what you're seeing on the axes. All right? Let me know if you have any troubles with them over the weekend. Thank you for your time. Good luck on your unit test. Happy fall break.